and welcome to my presentation on a project called SeagrassFinder, which is on deep learning for eelgrass detection and coverage estimation in the wild. This project is a collaboration of the IT University of Copenhagen and DHI Denmark, and it has received funding from REMARO, which is a European Union's Horizon 2020 research and innovation program. DHI is a water management company that monitors water quality in a range of different contexts. One of them is a new infrastructure project in the harbour of Copenhagen called Lynetteholm. This is a new artificial peninsula which will extend the coastline of northern Copenhagen and is planned to provide housing for around 35,000 people and also to protect the city from rising sea levels. DHI was assigned to supervise the construction and to oversee the water quality in the area. One way they achieve this is by monitoring the health of seagrass in the local environment. But why seagrass? Seagrass is fundamental for the health of marine ecosystems, providing food and shelter for fish and other aquatic organisms. Interestingly, seagrass is also 35% better at carbon sequestration than, for example, tropical rainforests. But a huge problem is that seagrass meadows are declining globally at an alarming rate, caused by coastal development, but also by bacteria and algae that are growing, caused by climate change. There are different types of seagrasses around Denmark. The most common type of seagrass is Zostera marina, or commonly called Eelgrass. It grows at a maximum depth of 50 meters. DHI conducts regular environmental impact assessments where seagrass health is used as a proxy metric for water quality. The way they achieve this is by doing transects of the underwater environment. Here, a camera is mounted onto a sled and towed behind a vessel to capture video footage underwater. The resulting images are then manually labeled on the presence or absence of seagrass. This is traditionally done by marine biologists, often in spreadsheets. This process is very labor-intensive, expensive, and slow, so there is a big interest in automating these processes, for example by applying deep learning or by deploying autonomous underwater vehicles. One of the difficulties with underwater images is that they can be heavily color distorted. This is because water particles block certain parts of the visual light spectrum the further you go underwater. Eelgrass grows up to a depth of roughly 15 meters, so the red and orange channels of the light spectrum are attenuated. Another difficulty of images of transect videos is that they have motion blur, which makes it quite difficult to detect the thin stalks of eelgrass. Here are a few examples from our dataset of images with and without eelgrass present. As you can see, it is difficult to determine the presence or absence of eelgrass even for the human eye. We not only want to know if there is eelgrass present or absent in an image, but also how much, since this density is also an indicator of the health of seagrass meadows. The problem is that visual coverage estimation is highly subjective, as shown in this photo guide. For example, it is quite easy to tell the difference between 25 and 95% coverage within this indicated square, but not so easy to tell the difference between 30 and 65% coverage, but the coverage has supposedly doubled in the image. And this is how this project SeagrassFinder started, with the objective to detect eelgrass and estimate eelgrass coverage in images. And our process is as follows. First, we extract the images from the transect videos of environmental impact assessments. Then we deploy a custom-made and effective annotation platform to have our images labeled. Then we apply transfer learning to train 4 types of deep neural networks and compare their performance. To acquire our dataset, we consider the transect videos of an environmental impact assessment from June 2023 in the harbour of Copenhagen, Denmark, covering an area of around 10 square meters. This image shows areas of unvegetated areas and areas with sparse or dense submerged aquatic vegetation in different shades of green. The transect lines in blue show the plant roots across the area of interest. We choose a subset of 6 transect videos for their high degree in variability in visual content, for example, changes in the seabed. We then deploy our own data annotation app, which is a Python Streamlit application hosted on Microsoft Azure. The aim was to create an intuitive and self-explanatory interface for a fast and efficient labeling process. Here you can see a screenshot of the instructions page. We wanted the users to focus on the visual instructions in the center of the screen. And here you can see the labeling page. We also added a leaderboard to the app to spark light competitiveness among the users. Our first result is a new dataset with 8,500 labeled images, which you can find on Zenodo on this QR code. We then apply transfer learning. This means that deep neural networks are pre-trained on generic datasets like ImageNet and then fine-tuned on our custom Eelgrass dataset. One thing we noticed is that ImageNet mainly contains images on land, so we were also curious to find out if our models show better performance if we pre-process our underwater images with an image enhancement tool. We train 4 kinds of models on this binary classification task: ResNet, InceptionNet, DenseNet, and Vision Transformers. And we consider 3 different metrics: test accuracy, ROC, and calibration error. Calibration error is the difference between predicted probabilities and actual observed frequencies, and high calibration error indicates over or underconfidence. Our results show that the image enhancement, here marked by ++, improves the performance of the deep neural networks in 26 out of 30 cases. Overall, the vision transformers show the best performance. Here you can see a transect video with the predictions of our vision transformer model overlaid as a post-processing step. You can see that our model is more confident when more eelgrass is present in the image. Now, to estimate the eelgrass coverage from our detections, we had to consider that our images have some specific properties. For example, our images are at an angle towards the sea floor, not top-down. Then we also have spatially overlapping frames because we look at an image stream or a video. So we decided that a good estimation could be the temporal mean over an image sequence. So for example, if you consider 4 instances at a time, in this case you would get 50% coverage. We estimate the coverage with a range of 30 samples for each location. Now, based on our eelgrass detection models, we can estimate the coverage around this section of the Copenhagen harbour. You can see the result in the heat map in the middle. Unfortunately, we do not have ground truth of the eelgrass coverage in this area, but we can compare it to the satellite images from before. For example, consider transect 9. You can see that our eelgrass coverage method manages to capture, for example, the distinct boundary between the unvegetated area and the densely populated area. There are some limitations to our method that we need to consider. In example 1, the top scene has less eelgrass than the bottom scene, but our temporal mean method gives the same coverage estimate. However, here it is important to note that our images are at an angle towards the sea floor, and because of the spatial dependency, we can still draw conclusions to the overall coverage in an image sequence, just based on our binary predictions. In example 2, you can see we might also lose some location information. We still think our method has several advantages. First, it is highly automated, scalable, and practical, once a suitable classifier is trained. Then it can potentially predict eelgrass coverage in real time and thus improve environmental impact assessments even during their execution. Then it is also potentially less biased than human labeling and thus more reliable and repeatable. If you would like to read the full paper, you can find it here on this QR code. Thank you for your attention.